Okay, in this screencast we're going to look at various types of gas laws. Here's the kind of questions we'll be asking. What happens if you pressurize a gas, like push on a syringe? What happens if you expand that gas? That means have the volume go up. What happens if you heat a gas? What will happen? And does it matter what the gas is? Do they all travel at the same speed, like different colored billiard balls? If you push them with the same force, they should go the same distance. Are gases like that too? Do they all travel at the same speed? And what about their volume? If you have a zillion molecules exactly of helium, will it have the same volume as that same number of molecules of methane, for example? These are things we'd like to know. Finally, what do gases in a three-dimensional game of pool have in common? I like to think of gases as being part of a three-dimensional swimming pool. It's a three-dimensional pool table, I should say, and that might help you understand the behavior of gases. This is Screencast 10.1. Okay, let's cover a lot of material about gases, and maybe the best place to start is to compare them to the other phases. Think of a gas, compare it to a liquid or a solid. What strikes you? Well, things that come to mind for me is they're way less dense, so much so that they hover about, don't they? They're about 1 gram per liter as opposed to a liquid, which can be 1 gram per milliliter for the case of water, for example, 1,000 times less dense. Strangely, they fill up a container regardless of the amount. That's because of this effect where they hover about and seem to just keep moving around. They're oftentimes invisible, and that can be frustrating. Since they don't partially fill anything, there's no reflection plane that you can see that you can with liquids when they half fill a cup of water, for example. Also, they react very quickly. Now let's consider their physical behavior. Let's imagine that you're pushing on a closed syringe barrel right here. Say you're going from 50 mils to 25 mils. What's going to happen? Well, you should feel huge resistance when you push it down like that. And that's because the pressure is increasing. As the volume goes down, the pressure goes up. A good rule of thumb is that whenever you have an inverse relationship, an up-down relationship like that, the before and after cases should be lined up and multiplicatively. Temperature shouldn't change for this as long as you do it slowly. Now, we wouldn't say the P1 over V1 equals P2 over V2, because that would be for a proportional relationship. We say P1, V1 equals P2, V2. This is Boyle's law. Imagine heating an expandable system like a piston here. Well, the volume's going to go up. It's going to expand. This would be true for a balloon. This would be true for a piston, any expandable system. It won't pressurize, at least not if there's no resistance here, because it can expand rather than pressurize. This became known as Charles' law, T1 over V1 equals T2 over V2. Here's a dangerous law. Heat a closed container. Bad idea. Never do this. As the temperature goes up, the pressure can go up. All containers have some sort of threshold pressure at which they will burst, and you don't want to exceed that. The volume won't change because these are fixed volume systems. Bottles, glasses, things like that. This became known as the law of Gay-Lussac. T1 over P1 equals T2 over P2. The original temperature divided by the original pressure is equal to the final temperature divided by the final pressure. I like this one. Take some ammonia gas and let it enter a glass tube going that way. At the same time, take some hydrochloric acid and let that gas enter that way. Will they meet dead in the center? If so, the identity of the gas shouldn't really matter. They all travel at the same speed, but they don't. The little guy went faster because over the same period of time, it went further. Thomas Graham eventually determined that the little gases move faster, but not that much faster. It's not proportional to their mass. It's proportional to the square root of their mass. Isn't that strange? The rate of the first one over the rate of the second one is inversely proportional to the square root of their molar masses. Another interesting tidbit. Does the identity of the gas matter? It turns out it doesn't. If you take the same number of molecules, 40 grams of argon, 28 grams of diatomic nitrogen molecules, or 2 grams of hydrogen molecules, those are all the same number of particles, right? You've got 6 times 10 to the 23rd, or 1 mole of these guys in either case, and they occupy the same volume. That's a biggie. Gas atoms have the same volume, so it wouldn't matter if it's a mixture. What is that volume? 22.4 liters. This is known as Avogadro's principle, sometimes Avogadro's law. A mole of a gas has 22.4 liters. Notice we have to establish some fixed parameters here, since the temperature and the pressure will change that volume. Standard temperature and pressure has been arbitrarily determined to be 0 degrees Celsius and 1 atmosphere. This is Screencast 10.1.